line. And in order for us to get started, we're going to have to kind of review our completing the square. And this is not going to be for equations per se, where you add something to both sides. We just have a trinomial that we need to reconfigure so that when we complete the square, it's going to look like some x value plus or minus some constant squared, and then there's going to have to be some sort of adjustment constant. So a perfect square is when we have like the same factor twice, but we're not going to be able to make that happen without adjusting what was given to us. So for example, if I take a look at x squared minus 10x plus 2, like there's no way for me to figure out like what times itself will give me this trinomial. So what we do instead is we take a look at just the variable terms and we make that piece a perfect square, and then we figure out what do we add or subtract so that we can make it equal to 2 after all. So for x squared minus 10x, I can make that be x minus 5 times itself. And so how I came up with that is I just took half of the negative 10. And so if I were to distribute this, I would get x squared minus 5x, and again, and then plus 25. So this part right here gives me the x squared minus 10x, which is perfect, right? Like that's where this is coming from, but this is not so perfect, right? Because I have a 2 here and I have a 25. So that's not working out. So what do I need to do to make that 25 into a 2? Because that's what I began with, and I would subtract 23. And so that is where I'm getting this right here. So again, if I were to distribute this, I would get x squared minus 10x, yes. But then I would get plus 25, no. So then I would subtract 23, okay? So let's take a look at this next one here. So again, so we start with just the variable pieces, x squared plus 8x, and I say, okay, that's going to factor out to x plus 4 squared. And again, I got the plus 4 because of the 8. Half of positive 8 is positive 4. So if I were to distribute this, I would get x squared plus 4x plus 16. But I don't want plus 16. I want a negative 9, right? So I don't want the 16. I want a negative 9. So what do I have to subtract from 16, right, to get negative 9? And that would be 25. So this would be 16 minus 25, which would give me the negative 9. Okay? All right, so let's take a look at another one. So again, we start with x squared minus 18x, so the variable piece. And I say, okay, what would that factor to if it were a perfect square? It would be x minus 9, because half of negative 18 is negative 9 times itself. And then I need to figure out what's going to go here so that I will end up with a 21 instead of an 81, right? So if I were to distribute that, I would get x squared minus 9x minus another 9x plus 9 times 9 is 81. 81 is not what I want. 21 is what I want. So I would have to subtract 60 from that to get 21. And so that would be my completing the square piece, right? Okay, so let's go on. So let's take a look at what if it has like a negative leading coefficient. So that's no worry there. So we would just factor the negative out. And then now we're just going to work on factoring or completing the square on the x squared minus 4x. So I would have that negative out. So I would take half of negative 4, which is negative 2, and then square it, right? And so if I were to distribute this part, I would get x squared minus 4x plus 4, which is not what I want, right? Because I want a plus 0. So what do I have to do to that 4 to make it a 0? I would subtract 4. So now if I were to distribute this out, I would get this beginning piece. Okay? All right. So I'm not going to do those other 2 examples, but feel free to do those yourself, and I will write down the correct answer, and then you can check it. Okay, so press pause, try it, and then give it a whirl. But meanwhile, I'll just write down the answer. Hopefully I can do this. There you go. Sorry, I had a little momentary lapse there. Okay, so hopefully you got those two there. All right, so let's go ahead and take a look at our integral patterns. So these are two new patterns for us. We did do the derivative version of these. So, maybe they look a little familiar. It's just that we had for the derivative version, it was just 1 was our A value. So because 1 was our A value, this does look a little bit different, but in general, they are the same kind of concept. So one thing we have to pay attention to is that u is our function of x. So u is our variable term. And then a being greater than 0 is our constant. And so we have to kind of keep track of that. And so we are, trying to pay attention to the fact that a is a constant value. And then u is our function of x. So u is our variable term, a is our constant. So we always are going to be striving to get it into the format that's here. And so this is where that completing the square is going to come into play. And so we want to have like our constant squared minus our variable term squared, our constant squared plus our variable term squared. So we're going to know when are we working with arctangent, when are we working with arcsine, based upon is it a subtraction problem, are we square rooting, or are we just addition, adding. Okay, so that's what we're looking for. So let's take a look at example 1, so for A. So for this one here, what we do want to make sure we are recognizing is that we have arctangent versus arcsine, and this would be arctangent. And so I want to put it in this format here. So for starters, I'm going to pull that 9 to the front, and I can do that because it's a coefficient. And so that would just be a 1 here. And then I want my constant term squared first, and then plus my variable terms squared second. So my constant is 16, so I'm going to rewrite that as 4 squared. And then my variable term is just x squared. So this is now in that a squared plus u squared form. So a would be the number being squared, u would be the variable term being squared, and then now compute your derivative to see if it lines up. So the derivative of x is just 1 or 1 dx. And so, which is what I have here, right? So I just have 1 dx, so perfect. So then I don't need to do a u to u substitution because the du dx matches perfectly, right? So now I'm going to go straight into that pattern. So I'm looking just to follow the pattern. So I have the 9 from the front, and then now I'm going to do 1 divided by a. So 1 divided by my value for a, which was 4. And then arctan, and then u divided by a is what comes after that. So u was x, and a was 4, and then of course my constant. And then I could leave it like that or write it as 9/4, but that would be it. Okay, so let's try B. So for this one here, the x cannot go to the front because it's a variable. So I'm going to move it over with the dx. So I want to keep it as that 1. And then I want my constant first, so 4, but I'm going to write it as 2 squared. And then plus, and then again, I want to write this as a squared as well. So that would be x squared squared. And then pull that x to the front. Or not to the front, but to the dx. Okay, so I have that 1 over piece. Okay, so the x slid over to the dx, not out front because it's a variable, so it needs to go to the dx. And then I rewrote this, so 4 became 2 squared, and then x to the 4th is x squared squared. All right, so a is the number value being squared, so that would be 2. U is the variable term being squared, so that would be x squared. And then now calculate that derivative. So the derivative of x squared is 2x dx. Okay, so far so good. So we're going to have to adjust just a tiny bit here, right? Because I have, instead of just a x dx over here, I have a 2x, right? So I need x dx. So I'm going to divide both sides by 2, and that's just so that they will line up. And then I'm going to go ahead and do a u to u substitution because it's not so perfect, right? Unfortunately. So we have the integral of 1 over 2 squared. And then x squared is u. And then x dx is going to be 1/2 du, but I will pull that 1/2 over. All right, so now we're going to just go right back up to here again and follow that pattern. So we have the 1/2 that we already had from the du dx substitution. And then now it's going to go to 1 over a, and a is 2, so 1 over a. And then arctan of u, which was x squared, over a, which was 2. And then again, I can multiply the 1/2s together to get 1/4, but I'll just leave it, okay? All right, so let's take a look at part C. So for this one here, I can see I have a square root with a subtraction, so that means I'm going to be working with arcsine this time. So I have that 2, which is a number value, so it can move to the front. And then 16, I'm going to write it as that squared term, so that would be 4 squared, and then minus x squared, and then dx. So from here, I'm going to do the same process again. So a is going to be the number value being squared, so that would be 4. And then u is the variable term being squared, which is x. And then let's take that derivative. So the derivative of x is 1, or 1 dx. And so whenever it works out perfect like that, I do like a little yay, because then I don't have to actually do a u to u substitution, because it works out beautifully. And so then now I just do my arcsine pattern. So notice that there's no 1 over a here. I didn't forget it. It's just not there. So I have the 2 that I'm going to bring down, and then it's going to be arcsine of u, which was x, over a, which was 4. And there's my arcsine pattern. Lovely. All right, so moving on. Okay, so here we go. So I'm going to do my rewrite. So cosine x is a variable term, so it doesn't get to go to the front. It gets to scooch over to the sine of x. So 1 is the same as 1 squared. And then sine squared of x is the same as sine of x quantity squared. So let me rewrite that. And then move that cosine x over to that dx piece so I can see how well they line up. And then let's go ahead and write out what is a, what is u, and then calculate my du. So a, the number value being squared, which is 1. U is the variable piece being squared, so that would be sine of x. And then now let's calculate that derivative. So the derivative of sine is cosine of x dx. And see how perfect that matches up? So yay! I just now do my substitution. So this is going to be an arctangent pattern because I have an a squared plus u squared. So I'm going to be back up into the arctangent. So that would be 1 over my value for a, which was just 1. And then arctangent of u, which was sine of x, over a, which was 1. And there you go. Perfect. Okay, so let's take a look at some with definite integrals. Okay, so same concept, right? So we're just doing definite integrals. So I am going to go ahead and rewrite this so that I have my a squared and u squared clearly defined. So that 1 is perfect. And then the square root. So 1 is just 1 squared. And then 9x squared would be 3x quantity squared, right? And then I just have a 1 dx. All right, so my a is my number value being squared, which is just 1. And then u is the variable term being squared, so that would be 3x. And then I have to calculate my derivative. So the derivative of 3x is 3 dx. And this is where boo, because I have a dx, not a 3 dx. So I'm going to divide both sides by 3. And then that means I have to do a substitution because they don't match up beautifully, right? So here comes my substitution. So I have 1 over, and then the square root of 1 squared. And then I'm going to replace 3x with u. And then dx, I'm going to replace with 1/3 du, but I'm going to go ahead and move that 1/3 out. And then I also have to do the limits in as well, right? Because these are in terms of x and I need to be in terms of u. So we'll just do that down here. So I'm going to start with, how about my upper limit? And so I'm going to use this right here to help me calculate my value for u. So that would be u equals 3 times pi over 3. So my upper limit would just be pi. And then let's do our lower limit, which is pi over 6. So that would be 3 times pi over 6, which would be pi over 2. There we go. All right, so now we're doing arcsine because I have that square root with a subtraction. So that 1/3 is just going to hang out in the front for a while. So let's do the pattern. So we have arcsine of u, which was 3x, over a, which was 1. And then our limits are from pi over 2 to pi. And then we'll just do upper minus lower. So I still have that 1/3. And so I would have arcsine of 3 times pi, and then minus arcsine again of 3 pi over 2. And that's it. Okay, so let's take a look at f here. So we have from 0 to 1, e to the x cannot go to the front, so I'm going to move it over with the dx. And then I want my constant term first, so I'm going to do the 1 first, so that'd be 1 squared. And then my variable term squared. So e to the 2x is the same as e to the x quantity squared, right? That means the same thing, because if I were to multiply those together, I would just get e to the 2x. And then again, I'm moving that e to the x over with the dx. Okay. All right, so my a value is the number being squared, so that would be 1. U is the variable term being squared, so that would be e to the x. And then now we're going to calculate the derivative. So that is just going to be e to the x times 1 and then dx. And then this is where I'm like, yay, there's my du. Perfect, no modification needed. So no modification means no substitution. I just saved myself a step. So let's go ahead and integrate this. So this is an arctangent pattern. So it's going to be 1 over a, and then arctan of u, which was e to the x, over a, which was 1. And then we're going from 0 to 1. So I'm going to go ahead and substitute in my limits. And then 1 over what is just 1. So I'm just going to have that as arctangent of e to the first, and then minus, and now substitute in 0. So that would be arctangent of e to the 0. And so then that's just arctangent or tangent inverse of e minus arctangent or tangent inverse of e to the 0, which is 1. So I don't know what arctangent of e is, and I certainly didn't know these other ones over here, but I do know the tangent inverse of 1. So I'm going to go ahead and do that just to remind you that this means at what value or what angle value is tangent equal to 1, and that is at pi over 4. And so I can have it like that as well. Okay? All right, so that's just kind of using the patterns. And then our last page here is working with that completing the square piece, which if you get the completing the square and you get what we just did, this will be relatively straightforward. Okay, so if I look at this, so it tells me to complete the square. So I'm going to go ahead and do that. And I don't need to do anything with the 1. And so I know that I have x squared plus 4x, so I start with that piece there. And so that will give me x plus 2 squared, right? Because that would be the x squared plus the 4x. And then when I distribute that, I would get 2 times 2, which is 4, but I don't want 4, I want 13. So I would need to add 9. Okay, so again, how did I do that? So half of 4 is 2, that's where that came from. My goal is when I distribute, I get a plus 13, but this would only give me a plus 4, so I need to add another 9 to get that 13. Okay, so I'm not going to rearrange this. Hopefully you can see what your A and your U are and all that. So A is my number value being squared. So if I have a 9 here, that makes my A being 3. So I'm not doing the rewrite piece. And then my U is my variable term squared, which is x plus 2. Then compute your derivative. So the derivative of x plus 2 is just 1 dx. And I get always excited, even if I don't sound like it in my voice, but I always get excited because that means I don't have to do a substitution or any modification. I just can go straight into the pattern. So that pattern, so this is arctangent, is going to be 1 over A, and then arctangent of U over A, and then plus C. Okay, let's do another. So that 3 is a coefficient, so yank it to the front. And then let's go ahead and complete the square down here. So I have x squared minus 6x, so that would be half of negative 6 is negative 3. And I need a 10 when I distribute this out. So that would give me the x squared minus 6x, but then negative 3 squared is 9, but I need a 10, so I'm going to add one more to make 9 plus 1 equal to 10. Okay? All right, so again, I'm not going to do the whole a squared u squared. We're going to do that just with our brilliant minds. So my a is the number value being squared, so that would be 1. 1 squared is 1. U is the variable term being squared, so that would be x minus 3. And then calculate the derivative. So the derivative of x minus 3 is 1, and then the dx. And then I'm like, yay, yay. So it matches perfectly, no substitution required, just follow the pattern. So I have the 3 to begin with. And then this is arctangent, so that would be 1 over a, which is 1 over 1. And then arctangent, or tangent inverse, of u, which was x minus 3 over a, which is 1. And feel free to rewrite that as 3 arctangent of x minus 3, all good. All right, last two. Okay. So we're going to do this one right here. And so on this one, I have that negative. So I'm going to, because I have the negative, I do that off to the side. So I'm going to pull that negative out first. So the square root is still there. I'm just working on just the underneath side piece here. Okay. So when I do that, I have x squared minus 4x. So now that's what I'm going to complete the square on. So I'm going to do half of negative 4. And then I want a 0, right? Because I'm not adding any number here, so 0. So that would be positive 4. So that means I would subtract 4 to make them equal. So if I were to distribute this, I would get x squared minus 4x. And then this would be plus 4 minus 4, which is 0. And then now I'm going to go ahead and distribute the negative in. So I would get negative x minus 2 squared plus 4. So let's go ahead and incorporate that now into the integral. So I'm going to pull that 2 out. And then this is under my square root, but because it's arc sine, I want my constant first. So that would be 4 minus x minus 2 squared, and then that's under the square root. Okay, so a little tricky there. So maybe pause, maybe look at that again one more time just to kind of make sure that that made sense to you, okay? And then I'm going to do my a terms down here. So my a is the number being squared, so that would be 2 squared because 2 squared is 4. U is the variable term being squared, so that would be x minus 2. And then that derivative is 1 dx, and yay, yay, right? Always be excited when that happens because that means you don't actually have to do a u to u substitution. All right, so let's go ahead and finish this out. So this is arc sine, so this would be 2. There is no 1 over a for arc sine. And then u, which was x minus 2, over a, which was 2, and then plus c. Bada bing, bada boom. Okay? All right, last problem. So this one's an oddball. Okay, this is an oddball problem. And you will see here shortly. Okay, so this one's like going to be joyous. All right, so it does in the direction tell me to do complete the square. So this 2x minus 5 is not a number value, so it's got to like head over to the dx. So give myself a little extra room here. And then let's go ahead and complete the square here. So that would be x plus 1 squared. And then, what is that, 1 plus 1? So plus 1. So half of 2 is 1, and then 1 squared is 1, but I need a 2, so add 1 more. All right, so my a value would be the number being squared, so that would be 1. Squared is 1. U is my variable term, right? So that would be x plus 1. And then that derivative is 1 dx. So this is where it gets a little like, uh-oh. Like you should be hopefully going, uh-oh, because my du is just dx, but my du over here is 2x minus 5. That's like a big uh-oh, because how do I turn this here into 2x minus 5 dx? I can't. Like that is like not going to happen. There's no way for that to happen. Like I cannot make that happen. So I have to like rethink what I'm going to do here, because that just isn't going to work, because I have a 2x minus 5, and that's very suspicious. So because of that, I'm going to do old school. Old school meaning just like 2 nights ago. I'm going to rewrite and pull that x squared up to the top. And then I'm going to say, okay, so we're going to let u equal the x squared plus 2x plus 2. And then du is going to be 2x plus 2. And then I'm going to go, oh, well, that's not too bad. So I have a 2x plus 2 here, but a 2x minus 5 here. That's close. What can I do to make that work? So here's going to be a little math magic. And I call it math magic because you probably wouldn't have come up with this on your own. So do keep that in mind. So if you're like, what just happened here? In about 2 seconds, don't panic, because we'll practice these, because this is definitely a little math magical, because you would probably not have come up with this on your own. Maybe you would have. I don't know. Maybe I'm not giving you enough credit. So I'm going to rewrite this because I want it to be 2x plus 2 because of that du. So I can't just randomly change 2x minus 5 into 2x plus 2. I mean, I can kind of, but I can't. And so let me show you my math magic. So what did I do here? So I said, okay, I need this to be 2x plus 2, so I'm just going to make it 2x plus 2, because that's what I need in order for this u to u to work. And I can only do that, though, if I make it equal to the original problem. And so if I do 2 and negative 7, that gave me negative 5. So if I were to add this first fraction with this second fraction, I would get my original one back. And so now that allows me to work through that problem that I had. And so then now I'm going to go ahead and distribute the integral sign, because I can do that over addition and subtraction, right? And then I'm going to go back and rewrite this one very similarly to this one here. Okay, so I'm going to pull that x squared up to the top. And then I'm going to go ahead and distribute the integral into here. And then this u du that I had up here, I'm going to now apply to this problem. So instead of the negative 1 being this polynomial, it's just going to be u to the negative 1, right? Because that's what u equals. And then both of those are my du. And then now I have this one over here to contend with. So I'm going to pull that negative 7 out to the front. And then now I need to think about, okay, what can I do for that side? Because I can't use the same u to u because I don't have that 2x plus 2. So then now this side over here is going to be completing the square, just like we've done on the last like half dozen problems. So this integral on the left, that's just the natural log of u. And then now I have minus 7, and then I'm going to complete the square over here. So that would be x plus 1 squared plus 1. And then now I can do my arctangent. So I'm going to go ahead and let you figure that one out. So I'm not going to walk through all the steps, but I am going to write down my final answer. So my final answer, you can go back and see if you can make that happen for yourself. But we will definitely be going over several of these because they can be a little tricky. Okay, and that is the end of that.